Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC. And in the second question, we'll find out the area of rectangle ABCD that blocks this circle. So we'll start with the first question. In the drawing, we have triangle ABC. Side BC equals to 2 units. Angle ABC equals to 60 degrees. Angle ACB equals to 75 degrees. And our mission is to find out the radius of this circle that is inscribed by triangle ABC. So we start with the first method, and here we'll do a construction from point C. We'll draw perpendicular on AB. Here from point C, we'll draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. So I will copy the right triangle, triangle ABD, this triangle in a new page, and we'll analyze the green right triangle, the triangle ABD. Okay. This is actually triangle BDC. We'll analyze the green triangle, triangle BDC. So this is the right green triangle, triangle BDC, that I copied from the original drawing. We know that in triangle BDC, the sum of its angles must be equal to 180 degrees. So which angles we have in triangle BDC? We have this angle that is equal to 60 degrees, plus this angle that is equal to 90 degrees, plus this angle that we will define as angle X. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here 60 degrees plus 90 degrees is 150 degrees, 150 degrees plus x in total must be equal to 180 degrees. Here we subtract 150 degrees from this equation and we'll get that the missing angle, angle x, is equal to 180 degrees minus 150 degrees is 30 degrees. Okay, I found out that angle x equals to 30 degrees. We will continue to focus on the right triangle, triangle BDC. In the right triangle, triangle BDC, here sinus 30 degrees is equal to BD over BC. Okay, I'll repeat again. In the right triangle, triangle BDC, sinus 30 degrees is equal to BD over BC. Sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2, and we get that 1/2 is equal to BD over BC. But BC equals to 2 units according to what is given as the equation, so we substitute BC by 2. Here we will multiply this equation by 2 and we'll get that BD is equal to 1 unit. So we actually found out that BD equals to 1 unit. So we continue to focus on the right triangle, triangle BDC. On the right triangle, triangle BDC, cosine 30 degrees is equal to DC over BC. Again, cosine 30 degrees equals to DC over BC. So here, cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC, but BC equals to 2 units, so we substitute BC by 2. So here, square root of 3 over 2 equals to DC over 2. We'll multiply this equation by 2, and we'll get that DC equals to square root of 3 units. Okay, we found out that DC equals to square root of 3 units. So here we can write down that DC equals to square root of 3 units. In the next step, we'll find out the size of angle BCD, the size of this angle. What is the size of angle? Actually, it is angle ACD. We'll find out the size of this angle, that is angle ACD. The size of angle ACD is equal to angle ACB minus angle DCB. Again, angle ACB minus angle DCB will give us the size of this angle, angle ACD. Angle ACB equals to 75 degrees. This angle, angle DCB, equals to 30 degrees according to what we have already found out. So 75 degrees minus 30 degrees it is equal to 45 degrees. Okay. So in the next step I will copy the right triangle ADC in a new page, and we will analyze triangle ADC. So actually this is the right triangle ADC that I copied from the original drawing. The sum of the angles in the right triangle ADC is equal to 180 degrees. So which angles we have in triangle ADC? We have this angle that is equal to 90 degrees plus this angle that is equal to 45 degrees plus this angle that we will define as angle X. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees plus angle X. In total, they must be equal to 180 degrees. Here we'll subtract 135 degrees from this equation, and we'll get that the missing angle X equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. Okay, it is equal to 45 degrees. So here, this angle X equals to 45 degrees. So here, in triangle ADC, those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in a triangle, there are equal sides. In front of this angle, we have side AD, while in front of this angle, we have side DC. And according to the rule that I mentioned, those two sides must be equal to each other because of the fact that they are located in front of equal angles. But you've already found out that DC equals to square root of 3 units. Here DC equals to square root of 3 units, and from this equation AD equals to DC equals to square root of 3 units, we will derive that AD is also equals to square root of 3 units. Okay, AD equals to square root of 3 units, so we can write here that AD equals to square root of 3 units. We will continue to focus on the right triangle ADC. In the right triangle ADC, we will implement the Pythagoras theorem here by PT. PT is a abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD squared plus DC squared. So AC squared equals to AD. So here I found out that AD equals to square root of 3 units. So AD equals to square root of 3 units, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC equals to square root of 3 units, therefore DC squared is square root of 3 squared, that is 3. So in total we found out that AC squared equals to 3 plus 3, that is 6. Here we take a root out of this equation number 1, and we get that AC equals to the square root of 6 units. AC equals to the square root of 6 units. So here you can write down that AC equals to square root of 6 units. Actually, we found out all the length sides of triangle ABC. Now we will implement a new rule for the radius of a circle that is inscribed by a triangle. According to the new rule, this is rule number 7, the radius of this circle that is inscribed by a triangle ABC equals to the area of triangle ABC that blocks the circle over the semi-perimeter of triangle ABC, and the semi-perimeter equals to the sum of its side lengths of triangle ABC over 2. Okay, so we can write down here that the radius of the circle of triangle ABC here it is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. Okay, I'll repeat again. The radius that we are looking for of this circle is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. So, what is the area of triangle ABC? The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. The area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of triangle ABC is equal to the base of the triangle. We take AB is the base of triangle ABC times the height to the base. The height to the base AB is DC. Why? Because it makes 90 degrees with the base AB. So the height is DC over 2. I'll repeat again. The area of triangle ABC equals to the base AB times the height to the base is DC over 2. So the area of triangle ABC is equal to AB. AB equals to 1 plus square root of 3 units times the height to the base. The height to the base, this equals to square root of 3 units over 2. Here we'll open the brackets in this equation and you get that the area of triangle ABC is equal to 1 times square root of 3 is square root of 3, and square root of 3 times square root of 3 is 3, so it is square root of 3 plus 3 over 2. Square root of 3 is 1.732 plus 3 over 2 is the area of triangle ABC. 1.732 plus 3 is 4.732 over 2, and 4.732 over 2 it is actually 3 plus 1.732 is 4.732 and 4.732 over 2 is equal to 2.366 square units. Okay, we found out the area of triangle ABC. Now the only thing that is left to do is to find out the semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter over 2. And the perimeter of triangle ABC, it is equal to the sum of its side lengths. That is to say, it is equal to AB plus AC plus BC over 2. I'll repeat again, the semi-perimeter of triangle ABC equals to the perimeter of triangle ABC, that is the sum of its side lengths, over 2. So here AB equals to 1 plus square root of 3 units plus AC equals to square root of 6 units and BC equals to 2 units. So all divided by 2. So the semi-perimeter triangle ABC equals to 1 plus 2 is 3 plus square root of 6 plus square root of 3 over 2. So here S equals to square root of 6, square root of 6 is actually 2.449 plus square root of 3 plus 3 over 2, and it is equal to 3.59 units. So S equals to 3.59 units. And again, the radius of this circle that is inscribed by triangle ABC will be equal to 'The area of triangle ABC over the semi-perimeter of triangle ABC. That is to say, the area of triangle ABC is 2.366 square units over the semi-perimeter of triangle ABC, that is equal to 3.59 units. And here it is equal to 0.6589 units. So the radius of the circle that is inscribed by triangle ABC equals to 0.6589 units. Okay, so we finished with the first method. In the next step, I present to you the second method to find out the radius of this circle that is inscribed by triangle ABC. In the second method, we define the center of this circle as point O. We define the point of tendency of tangent BC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is a point on the circle itself, therefore OF is the radius of the circle. We define the radius of the circle as R, so OF equals to R. And here we have the radius that is going to the point of tendency. That is to say, it is going to point F, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is going to the point of tendency, then tangent BC will be perpendicular to the radius FO. So if BC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. A tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the next step, we join points O and C together by a straight line. We join points O and B together by a straight line. We define the point of tendency of tangent AB with this circle as D. We join points O and D together by a straight line. O is the center of the circle, point O is the center of the circle, point D is the point on the circle itself, therefore OD is the radius of the circle that is equal to R. Here again, we have the radius of OD that is known to the point of tendency, that is to say it is known to point D, that is the point of tendency of tangent AB with this circle. Therefore, tangent AB will be perpendicular to the radius DO. So, that is to say this angle equals to 90 degrees according to rule number 1, and this angle also equals to 90 degrees according to rule number 1. We'll define the point of tendency of tangent AC with this circle SE. We join points O and D together by a straight line. Again, point O is the center of the circle. Point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R. And again, we have the radius OE that is known to the point of tendency, therefore tangent AC will be perpendicular to the radius OE. That is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, I present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, tangent PA equals to tangent PB in its lengths. So we can implement rule number 2 in our drawing. Why? Because in our drawing we have the common external point B. From the common external point B, we have two tangents to this circle, tangent BD and tangent BF. And according to rule number 2, they must be equal to each other. That is to say, BF is equal to BD. Likewise, we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CF and tangent CE. And according to rule number 2, they are equal to each other. So that is to say, CF equals to CE. So in the next step, we will prove that the green triangle BOF, this green triangle, congruent to the orange triangle DOB. So I write it down. The green triangle is triangle BOF. Is congruent to the orange triangle BDO. So why those two triangles congruent to each other? First of all, we just right now prove that side BD equals to side BF equals to side BD according to rule number 2. BD equals to BF according to rule number 2. In addition, DO equals to DF, they are both the radii of the circle. They are equal to R. DO equals to OF equals to R. And finally, OB is the common side that belongs to both triangles. Therefore, OB equals to itself. OB equals to OB. It's a common side that belongs to both triangles. So I actually found out that the green triangle is congruent to the orange triangle, triangle BOF, congruent to the orange triangle, triangle BOD, according to side rule. And for the fact that those two triangles congruent to each other, we conclude that those two angles are equal to each other. That is to say, angle OBD is equal to this angle that is actually angle OBF. Why? According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles must be also equal to each other. So, and if we define one of those angles as alpha, here angle OBD equals to alpha, then from this equation we will derive alpha equals to angle OBD equals to angle OBF. From this equation we will derive that the angle OBF is also equals to alpha. Angle OBF equals to alpha. So both angles here are equal to alpha. And the sum of those two angles is alpha plus alpha. And alpha plus alpha must be equal to 60 degrees according to what is given as the question. Alpha plus alpha is 2 alpha. 2 alpha equals to 60 degrees. We divide this equation by 2 and we get that angle alpha equals to 30 degrees. Here this angle alpha equals to 30 degrees, and this angle alpha, it is also equals to 30 degrees. Likewise, those two triangles will be also equal to each other according to side rule. Maybe I will not repeat on the same process again in order to shorten the lecture. So those two triangles are also equal to each other according to side rule. Therefore those two angles must be also equal to each other. And the sum of those two angles is 75 degrees, so each angle must be equal to half of 75 degrees, that is 37.5 degrees. This angle equals to 37.5 degrees, and this angle also equals to 37.5 degrees. Okay? So we'll focus on the green triangle. In the green triangle, triangle BOF, the green right triangle BOF, triangles 30 degrees, equals to OF over BF. OF equals to R, BF is the missing line segment, triangles 30 degrees equals to R over BF. So here we'll multiply this equation by BF and we'll divide it by tangent 30 degrees, and we'll get that BF equals to R over tangent 30 degrees in the next step. We'll focus on the right triangle, the yellow right triangle OFC. In the yellow right triangle OFC, tangents 37.5 degrees is equal to OF over FC. So tangents 37.5 degrees is equal to OF. OF is R, so we substitute OF by R over FC. Here we multiply this equation by FC and then we divide it by R, and we'll get that FC equals to R over tangents 37.5 degrees. Okay, actually we found out the values of FC and BF. And what is the value of BC? From the drawing it is very easy to see that BC equals to BF plus FC. I'll repeat again. BC equals to BF plus FC. So BC equals to BF, that is R over tangents 30 degrees, plus FC. FC equals to R over tangents 37.5 degrees, so in conclusion, I found out that BC equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. Here we take out R as a common factor from those two expressions, and we'll get that BC is equal to R. What is left from this expression after we took R as a common factor? What is left? It is actually 1 over tangents 30 degrees. And what is left from this expression after we took from it R as a common factor? What is left is actually 1 over tangents 37.5 degrees. So here we calculate the value of 1.1 over tangents 30 degrees, and also the value of 1 over tangents 37.5 degrees, and we will add them together. This way we find out the radius of this, the radius of the circle. So BC equals to R, and here tangents 30 degrees equals to so here this expression 1 over tangens 30 degrees in total equals to 1.732 units plus 1 over tangens 37.5 degrees. This expression equals to 1.303 units, and here the sum of those two expressions is actually 3.035 units. So BE equals to R times 3.035 units, but BC equals to 2 units, so we substitute BC by 2. We'll divide this equation by 3.035 units, and finally we'll get that R equals to 2 over 3.035 units. That is to say, R, that is the radius of the circle that is described by triangle ABC, it is equal to 0.6589 units. So in both methods we arrived to the same result. So we finished with the first question. In the next step, I present to you the second question, and we'll solve the second question in two different methods. In the drawing, we have rectangle ABCD. Inside the rectangle ABCD, we have this circle. Chord PS equals to 6 units. Line segment SQ equals to 5 units. And our mission is to find out the area of rectangle ABCD. So, first of all, we will define the center of this circle as point O. We'll join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. We define the radius of the circle as R. Point P is the point of tendency of tangent BC with this circle. We have the radius that is drawn to the point of tendency, therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We will define the point of tendency of tangent DC with this circle as point F. We will join points O and F together by a straight line. Point F is the point of tendency of tangent DC with this circle. Point O is the center of the circle. Point F is the point of the circle itself, therefore OF is the radius of the circle, that is R. We have the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F, that is the point of tendency of tangent DC with this circle. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle, it is also equals to 90 degrees. In quadrilateral OPFC, again in this quadrilateral we have 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees. So this angle must be also equal to 90 degrees because of the fact that the sum of the angles in any quadrilateral equals to 360 degrees, and in order to complete the sum of the angles to 360 degrees, this angle must be equal to 90 degrees. So here we have rule number 4. According to rule number 4, the perpendicular from the center of a circle to a chord bisect the chord. Here the perpendicular OM to chord CD bisect chord CD. That is to say, CM equals to MD. We'll implement rule number 4 in our drawing. We have from the center of this circle, that is point O, we will draw perpendicular on chord SP. So here, this angle equals to 90 degrees, and this angle, it is also equals to 90 degrees. According to our construction, we'll define the touching point of the perpendicular from point O and chord FC as M, and according to rule number 4, SM equals to MP. SM equals to MP. SM equals to MP. So if we define SM as X, SM equals to X, from this equation X equals to SM equals to MP, we derive that MP is also equals to X. MP equals to X. That is to say, therefore, X plus X is SP. X plus X equals to SP. X plus X equals to SP, and SP equals to 6 units. According to what is given as the equation, X plus X is 2X. From this equation, we derive that 2X equals to 6. We divide this equation by 2, and we get that X equals to 3 units. So here, X equals to 3 units, and here also X equals to 3 units. Okay. In the next step, from point Q, we'll draw perpendicular on BC. From point Q, we'll draw perpendicular on BC. That is to say, here, this angle, it is equal to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as L. So here we define the intersection point between perpendicular QL and the radius QF as N. So here in quadrilateral OPNL, this quadrilateral, we have 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in the quadrilateral to 360 degrees. This angle must be equal to 90 degrees. Therefore, in quadrilateral QP and L, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral OP and N as a rectangle. I repeat again, quadrilateral OPNL is a rectangle. Why? Because it has 4 right angles, and we have the rule that the opposite sides of a rectangle are parallel to each other. That is to say, in rectangle OPNL, side OP is parallel to side NL. Side OP is parallel to side NL, according to the rule that the opposite sides of a rectangle are parallel to each other. Okay, here, but what is NL? NL is part of QL. You can see from the drawing that NL is part of QL, and here NL is part of QL, and QL is the perpendicular from point Q. So QL is a perpendicular, it is absolutely a straight line. So you can write down that QL is a straight line, it's a perpendicular. So we know that QL is a straight line, and NL is part of QL. And if a part of a straight line is parallel to another straight line, the straight line itself must be also parallel to the other straight line. That is to say, QL must be also parallel to QP. So you can write down that QL is parallel to QP. Here, QL is parallel to QP. And from the fact that QL is parallel to QP, we have here rule number 7. That states, according to rule number 7, actually it is rule number 9, that states that alternating angles between parallel lines are equal to each other. Those two pink angles are defined as alternating angles, and therefore they are equal to each other because of the fact that they are located between the parallel lines A and B. Okay, so we can implement rule number 9 in our drawing. Why? Because in our drawing we have those two angles that are defined as alternating angles, and they are located between the parallel lines QP and QL, and therefore they are equal to each other. So we can write down that according to rule number 9, angle OPQ, this angle OPQ, this angle is equal to this angle, that is actually angle LQP. I repeat again, angle OPQ is equal to angle LQP according to rule number 9. So if we define angle LQP as theta, here this angle equals to theta, and QP, that from this equation angle OPQ equals to angle LQP equals to theta, we derive that angle OPQ is also equals to theta. This angle OPQ is also equals to theta. Okay. So here in quadrilateral ABLQ we have 1, 2, 3 right angles. Therefore the fourth angle, that is this angle, must be also a right angle. So quadrilateral ABQL is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. We define side AB as A, we define side BC as B, BC is equal to B, it is also the diameter of the circle. So in rectangle, therefore here OP, that is the radius of the circle, equals half of the diameter. So if the diameter is B, then the radius must be equal to B over 2. So AB equals to A. And the opposite sides of a rectangle ABQL are equal to each other. That is to say AB equals to QL. But AB equals to A, therefore QL must be also equal to A. Okay, QL equals to A. So in the next step, we'll focus on the right green triangle OMP. So I copy triangle OMP in the new page and we'll analyze triangle OMP. MP equals to 3 units. The hypotenuse OP equals to B over 2. And angle MPO equals to theta. Okay, so in the right triangle OMP. So here, this is the right triangle OMP that I copied from the original drawing. In this right triangle OMP, cosine theta equals to MP over OP. Cosine theta equals to MP over OP. MP equals to 3 units, we substitute MP by 3. OP equals to B over 2, we substitute OP by B over 2. Here we'll move to the numerator. In the numerator we have 2 times 3, that is 6. We'll move B to the denominator here, so it is 6 over B. So in conclusion, we found out that cosine theta, according to equation number 1, equals to 6 over B. In the next step, we'll focus on the right big triangle QPL. In the right big triangle QPL, what is the value of cosine theta? Cosine theta is equal to QL over QP. Okay, cosine theta in the right triangle QPL is equal to QL over QP. QL equals to A, according to what we have already found out. QP, here QP equals to 5 plus 6. 5 plus 6, that is 11. So, in conclusion, we found out that cosine theta, according to equation number 2, equals to A over 11. So, here we have two different expressions for cosine theta. Therefore, we'll create equation number 3 that states that cosine theta, according to equation number 1, must be equal to cosine theta according to equation number 2. Okay? Cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. So cosine theta according to equation number 1 is 6 over b, and it must be equal to cosine theta according to equation number 2, that is A over 11. So here we found out that according to equation number 3, 6 over b equals to A over 11. Here we cross multiply this equation number 3, and we get that AB equals to 11 times 6 is 66. AB equals to 66. And we know that the area of rectangle ABCD is equal to the width and the length of the rectangle times the width. It is the area of an rectangle, and the length of rectangle ABCD is AB. The width is BC, and according to our definition, AB equals to A and BC equals to B, and we have already found out that AB equals to 66. AB equals to 66. So in conclusion, we found out that the area of triangle ABCD equals to 66 square units. Okay, the area of this triangle ABCD equals to 66 square units. We finished with the first method. In the next step, I will present to you the second method to find out the area of this rectangle ABCD. Again, we define the center of this circle as point O. We will join points O and P together by a straight line. I will not repeat on the same things that we did in the first method. OP is the radius of the circle. The radius is drawn to the point of tendency. Here, therefore, this angle equals to 90 degrees according to rule number 1. This angle also equals to 90 degrees according to rule number 1. We define AB as A and BC as B. B is also the diameter of the circle. We'll extend the radius PO until it intersects with side AD of rectangle ABCD. we know that all the angles inside a rectangle are right angles. So this angle equals to 90 degrees. This angle is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle, it is also equals to 90 degrees. So in rectangle A, B, we define the touching point of the extended PO and side AD as point F. In rectangle ABFP, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Side AB equals to A according to our definition. The opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side FP. But side AB equals to A, and therefore side FP must be also equal to A. Okay. We define the touching point between the extended PO and this circle as point M. What is the definition of chord MP? Chord MP passes through the center of the circle. Any chord that passes through the center of the circle is the diameter of the circle. So chord MP is the diameter of the circle. Chord MP is the diameter of the circle. And we already found out that the diameter of the circle equals to B. In the next step, we'll join points M and S together by a straight line. By joining points M and S by a straight line, we created peripheral angle MSP. Peripheral angle MSP rests on MP, that is the diameter of the circle. And we actually have rule number 5 that states that any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. So here, peripheral angle AMB rests on AB, that is the diameter of the circle, therefore it is equal to 90 degrees, as you can see from the drawing. We can implement rule number 5 in our drawing. Peripheral angle MSP rests on MP, that is the diameter of the circle, therefore according to rule number 5, it is equal to 90 degrees. Okay, we define this angle MPS as theta. In the right triangle MSP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, because of the fact that 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. But before that, here we have quadrangle FPDC. In quadrangle FPDC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in quadrangle FPDC to 360 degrees, this angle must be equal to 90 degrees. Okay, so we focus on triangle FQP. In the right triangle FQP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees minus theta. In order to complete the sum of the angles in this triangle to 180 degrees, this angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the green right triangle MSP is similar to the big big right triangle PFQ. So I write it down. We'll prove that the big right triangle PFQ is similar to the small green right triangle PMS. So why those two triangles are similar to each other? First of all, we just write down found out that those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, angle FQP is equal to this angle, that is actually angle SMP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again, angle FQP equals to angle SMP equals to 90 degrees minus theta. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So here, angle QFP of the big right triangle is equal to this angle, that is actually angle MSP. They are both equal to 90 degrees, therefore they are equal to each other. Okay, angle QFP equals to angle MSP equals to 90 degrees. And finally, this angle theta is a common angle, therefore it belongs to both triangles, so we can write down that angle theta equals to itself. Angle FPQ is equal to angle MPS equal to theta. It's a common angle that belongs to both triangles. Angle FPQ equals to angle MPS that is equal to theta. It's a common angle that belongs to both triangles, so we actually prove that the big right triangle FPQ is similar to the small green right triangle MPS, according to angle similarity rule. Okay, and for the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that FP over SP is equal to QP over MP. From the fact that the two right triangles are similar to each other, we conclude that FP over SP equals to QP over MP. What is the value of FP? We have already found out that the value of FP equals to A. So we substitute FP by A. over SP. SP equals to 6 units according to what is given as the question. So we substitute SP by 6 and it is equal to QP. What is the value of QP? QP equals to 5 plus 6, that is 11. We substitute QP by 11 over MP. The value of MP is the diameter of the circle, that is equal to B, so we substitute MP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we find out that AB equals to 6 times 11, that is 66. So AB equals to 66, and the area of rectangle ABCD is equal to the length of the rectangle, that is AB, times the width, that is BC. According to our definition, AB equals to A and BC equals to B. So the area of triangle ABCD, and we have only ABCD. The area of triangle ABCD equals to AB, and we just right now found out that AB equals to 66. So in conclusion, we found out that the area of triangle ABCD, it is equal to 66 square units. We finished with the second method. In the next step, I will summarize the lecture. We'll start with the first question, of course. So here, the drawing, we have triangle ABC. Triangle ABC blocks the circle, or the circle is inscribed by triangle ABC, and our mission is to find out the radius of this circle. We know that side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. In the first method, from point C we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. I copied the green triangle BDC in new page, and we analyze triangle BDC. This is the right triangle BDC that I copied from the original drawing. This angle equals to 60 degrees, this angle equals to 90 degrees, and we know that the sum of the angles in any triangle is 180 degrees. So the sum of the angles in triangle AB and BDC is 60 degrees plus 90 degrees plus this angle, that is the missing angle. We define the missing angle as x. So the sum of those two angles must be equal to 180 degrees. 60 degrees plus 90 degrees is 150 degrees, and 150 degrees plus x must be equal to 180 degrees. We subtracted 150 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 150 degrees. This is 30 degrees. So this angle equals to 30 degrees. We continue to focus on the right triangle BDC. In the right triangle BDC, sinus 30 degrees equals to BD over BC. Again, sinus 30 degrees equals to BD over DC. And sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2. So 1/2 equals to BD over BC, but BC is 2, so we substitute BC by 2. We got that 1/2 equals to BD over 2. We multiply this equation by 2 and found out that BD equals to 1 unit. Here BD equals to 1 unit. Then cosine theta in triangle BDC equals to DC over BC. DC over BC. So cosine, this cosine 30 degrees, that is equal to DC over BC. But cosine 30 degrees is square root of 3 over 2. Substitute cosine 30 degrees by square root of 3 over 2. And it is equal to DC over BC. BC is 2, so we substitute BC by 2. And we got this equation, the square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then we found out the size of this angle, angle ACD. What is the size of angle ACD? Angle ACD equals to angle ACB, that is 75 degrees, minus angle DCB, that is 30 degrees. 75 degrees minus 30 degrees is 45 degrees. Then I copied the right triangle ACD in a new page and analyze triangle ACD. This is the right triangle ACD that I copied from the original drawing. In the right triangle ACD, the sum of the angles must be equal to 180 degrees. So which angles we have triangle ADC? We have this angle that is equal to 90 degrees, this angle that is equal to 45 degrees, plus this angle that is the missing angle that will define this angle x. In total, the sum of its angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus angle x in total must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle, angle x, equals to 180 degrees minus 135 degrees is 45 degrees. So we actually found out that those two angles, they are both equal to 45 degrees, and we have the rule, therefore they are equal to each other. Therefore we have the rule that in front of equal angles in the triangle, there are equal sides. In front of this angle, we have side DC. In front of this angle, you have side AD, and those two sides must be equal to each other because of the fact that they are located in front of equal angles. But we have already found out that DC equals to square root of 3 units, so we can write in that DC equals to square root of 3 units, and from this equation AD equals to DC equals to square root of 3 units, we will derive that AD is also equals to square root of 3 units. Here AD equals to square root of 3 units. Then we implemented the Pythagoras theorem on the right triangle ADC in order to find out the length of the hypotenuse AC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, the square of the hypotenuse is AC squared, and it must be equal to AD squared plus DC squared. So AC squared equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared, DC is equal to 3, and the square root of 3 squared is 3. So in conclusion, we found out that AC squared equals to 3 plus 3, that is 6. We took a root out of this equation, equation number 1, and found out that AC equals to square root of 6 units. Here, AC equals to square root of 6 units. So we have the lengths of all the sides of triangle ABC. Therefore, we implemented here a new rule that gives us the radius of any circle that is inscribed by a triangle. The radius of any circle that is inscribed by a triangle, it is equal to the area of the triangle that blocks the circle over the semi-perimeter of the triangle. The semi-perimeter is the perimeter over 2. The area of triangle ABC, it is equal to the base times the height over 2. We took the base as AB, and the height to the base is CD over 2. So the area of triangle BC equals to AB times DC over 2. AB is equal to 1 plus square root of 3, and DC is square root of 3. Okay, so we got this equation. 1 plus square root of 3 times square root of 3 over 2 equals to the area of triangle ABC. We open the brackets here. 1 times square root of 3 is square root of 3, and square root of 3 times square root of 3 is 3. So in total, we found out that the area of triangle ABC equals to square root of 3 plus 3 over 2. Square root of 3 plus 3 is 1.732, plus 3 is 4.732 over 2 is 2.366. So we found out that the area of triangle ABC is 2.366. Then we found out the semi-perimeter of triangle ABC. The semi-perimeter of triangle ABC equals to the perimeter of triangle ABC over 2. The perimeter is AB plus AC plus BC, and if we divide it by 2, we will get the semi-perimeter. AB equals to 1 plus square root of 3 units, AC equals to square root of 6 units, and BC equals to 2 units. So if we add the three numbers together and we divide it by 2, we get that the semi-perimeter of triangle ABC is 3.366 for 3.59 units. So the radius of the circle that is inscribed by triangle ABC equals to the area of triangle ABC of the semi-perimeter over the semi-perimeter of triangle ABC. The area of triangle ABC is 2.366. The semi-perimeter of triangle ABC is 3.59. We divided the two numbers by each other and found out that the radius of the circle that is inscribed by triangle ABC equals to 0.6589 units. The radius of the circle equals to 0.6589 units. We finish with the first method. Then I presented to you how to find out the radius of the circle that is inscribed by triangle ABC according to the second method. In the second method, we used the rule number 1, tangent to a circle is perpendicular to the radius going to its point of tendency, and also rule number 2, that the lengths of two tangents from a common external point to a circle are equal. We define the center of the circle as point O. We draw those two lines. This angle, all the angles here are equal to 90 degrees according to rule number 1. And here, from point B, we have two tangents to the circle, therefore BD equals to BF according to rule number 2. And from the external point C, we have tangent CF and tangent CE. They are equal to each other according to rule number 2. Here, the orange triangle is congruent to the green triangle according to side rule. Why? We have a common side that is OB, it is equal to itself. Those two sides are both the radii of the circle, therefore they are equal to each other. And we just right now found out that side BD is equal to side BF according to rule number 3, therefore those two triangles can go to each other according to side rule. And from the fact that the two triangles can go into each other, we conclude that those two angles are equal to each other. If those two angles are equal to each other, each angle equal, and the sum of those two angles is 60 degrees, it means that each angle equals to 30 degrees. We actually know that those two triangles are also equal to each other according to the same rule, side rule. It is exactly the same things that we did here. We will not repeat on it. Therefore, those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if the sum of the two angles is 75, it means that each angle must be equal to 37.5 degrees. Okay. Then if we focused on the green triangle BOF, in the green triangle BOF, tangents 30 degrees equals to OF over BF. Tangents 30 degrees equals to OF over BF. OF equals to R over BF. So tangents 30 degrees equals to R over BF. Then we multiplied this equation, so tangents 30 degrees equals to R over BF. We multiplied this equation by BF and then we divided by tangents 30 degrees and found out that BF equals to R over tangents 30 degrees. Then we focused on the yellow triangle OFC. The yellow triangle OFC, tangents 37.5 degrees equals to OF over FC. Tangents 37.5 degrees equals to OF over FC. So tangents 37.5 degrees equals to OF. O equals to OF, that is R, over FC. So In conclusion, found out that tangent 37.5 degrees equals to R over FC. We multiply this equation by FC and then we divided it by R, and we got that FC equals to R over tangent 37.5 degrees. And what is the value of, what is the length of side BC? The length of side BC is BF plus FC. BF plus FC equals to BC. Repeat again. BC equals to BF plus FC. We already found out that BF equals to R over tangent 30 degrees and FC equals to R over tangent 37.5 degrees. Okay, then we took a common factor from those two expressions. What is left from R over tangent 30 degrees after we took from it R as a common factor? What is left is 1 over tangent 30 degrees. What is left from R over tangent 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 37.5 degrees. So here 1 over tangent 30 degrees equals to 1.732, and 1 over tangent 37.5 degrees equals to 1.303, and 1.732 plus 1.303 equals to 3.0335 units. So we found out that 2 equals to R times 3.035 units. We divided this equation by 3.0535 units, and we got that the radius of the circle equals to 0.6589 units. We finished with the second method. Then I presented to you the second question, and we also solved the second question in two different methods. So here in the drawing we have triangle ABCD. Inside triangle ABCD we have this circle that is blocked by triangle ABCD, and we also know that chord PS equals to 6 units, line segment SB equals to 5 units, and our mission is to find out the area of rectangle ABCD. So here we define the center of the circle as point O. We define here point P is the point of tendency of tangent BC with this circle. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point on the circle itself. Therefore, OP is the radius of the circle. And we have the radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then we define the point of tendency of tangent DC with this circle as F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point on the circle itself. Therefore, OF is the radius of the circle that is equal to R. We have the radius OF that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We know that all the angles inside a rectangle are right angles. Okay, and here inside a quadrilateral OPFC we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Okay, then I presented to you rule number 4. According to rule number 4, the perpendicular from the center of a circle to a chord bisect the chord. Here, the perpendicular OM from the center of the circle, that is O, bisects chord CD. That is to say, CM equals to MD. Implemented rule number 4 in our drawing. From the center of the circle, we draw perpendicular on chord PS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to rule number 4, perpendicular OM bisects chord SP, that is to say SM equals to MP. Okay, SM equals to MP, and if SM equals to X, then MP must be also equal to X because they are equal to each other. So we can write down that X plus X equals to SP, that is to say 2X equals to 6. We divided this equation by 2 and found out that X equals to 3 units. Here X equals to 3 and X equals to 3. Okay, then from point Q we go perpendicular on BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as L. So here we created quadrilateral OPML. Inside quadrilateral OPML we have 1, 2, we have inside quadrilateral OPLM we have 1, 2, 3 right angles. Okay, actually we have already found out that OPFC is a rectangle because OPFC quadrilateral OPCF has 1, 2, 3 right angles. Therefore the fourth angle must be equal to 90 degrees. So this angle must be equal to 90 degrees. So inside quadrilateral OPNL we have 1, 2, 3 right angles. Therefore this angle must be also equal to 90 degrees. Therefore inside quadrilateral OPNL we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So quadrilateral OPNL is a rectangle, and we know that the opposite sides of rectangle OPNL are parallel to each other. Okay, therefore OP is parallel to NL. OP is parallel to NL according to the rule that the opposite sides of a rectangle are equal to each other. So here QL is perpendicular to BC. So QL is a perpendicular, it must be a straight line. So here QL is a straight line, and NL is part of the straight line QL. And if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to that straight line. That is to say, QL must be also parallel to OP. QL is parallel to OP. Then I presented to you rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Line A is parallel to line B, therefore the two alternating angles in the orange color are equal to each other. Okay, we can implement rule number 9 in our drawing. We have those two angles that are located between the parallel lines OP and QL. Therefore, they must be equal to each other according to rule number 9. Okay, so angle OPQ must be equal to angle LQP. And if we define one angle as theta, then the other angle must be also equal to theta, because they are equal to each other. So those two angles are both equal to theta. Okay. Then I copied the right green triangle OMP in a new page, and we analyze triangle OMP. In the right triangle OMP, cosine theta equals to MP over OP. Cosine theta equals to MP over OP. MP equals to 3, OP equals to B over 2. 3 over B over 2 is 6 over B. 2 moves to the numerator, 2 times 3 is 6, and B moves to the denominator. So in total we get that cosine theta equals to 6 over B. Then we focused on the right big triangle QLP. In the right big triangle QLP, cosine theta equals to QL over QP. Cosine theta equals to QL over QP. QL equals to A and QP equals to 5 plus 6, that is 11. QL equals to A and QP equals to 11. So in total we found out that cosine theta equals to A over 11 according to equation number 2. Then we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 is 6 over B, and it must be equal to cosine theta according to equation number 2, that is A over 11. We cross multiply this equation number 3 and found out that AB equals to 66 units. The area of any triangle is the length of the triangle times the width. The length of triangle BCD is AB, the width is BC, AB equals to A and BC equals to B according to our definition, and we just right now found out that AB equals to 66 square units. So in conclusion we found out that the area of triangle ABCD equals to 66 square units. We finished with the first method, then I presented to you the second method. In the second method, we define the center of the circle as point O, AB equals to A, BC equals to B, and B also, it is also the diameter of the circle, and here we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. This angle equals to 90 degrees, this angle also equals to 90 degrees according to rule number 1. I will not repeat on the same process that we did in the first method. All the angles of triangle ABC of rectangle ABCD are right angles, so those two angles are all right angles. And here we extended the radius PO until it intersects with the circle as point until it intersects with side AB of triangle ABCD is point F. Okay, so in quadrilateral ABPF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, in quadrilateral ABFP, we have 4 right angles. Therefore, quadrilateral ABFP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. AB equals to A, therefore FP that is equal to AB must be also equal to A. Likewise, in quadrilateral FPDC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore also quadrilateral FPDC is also a rectangle. And here we join points M and S together by a straight line. In this way, we created peripheral angle MSP. In peripheral angle MSP, rests on MP, that is the diameter of the circle. Why MP is the diameter of the circle? Because it is a chord that passes through the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. So MP is the diameter of the circle, that is equal to B. And peripheral angle MSP rests on MP, that is the diameter of the circle, and we have rule number 5, that any peripheral angle that rests on the diameter of the circle is equal to 90 degrees. Here, peripheral angle AMP rests on AB, that is the diameter of the circle, therefore it is equal to 90 degrees. You can implement rule number 1 in our drawing. Peripheral angle MSP rests on the diameter of the circle, therefore it is equal to 90 degrees. Then we define this angle as theta. So this angle is theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Here this angle is theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta in the big right triangle FQP. Then we proved that the green triangle is similar to the big right triangle FPQ. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. Those two angles are both equal to 90 degrees, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So we actually proved that those two triangles can go into each other according to angle rule. And from the fact that those two triangles can go into each other, we conclude that the following relationship exists between their sides. We conclude that FP over SP equals to QP over MP. Here FP equals to A, according to what we have already found out. So we've substituted FP by A. SP equals to 6 units according to what is given as the question. QP, what is QP? QP equals to 5 plus 6, that is 11. And MP is the diameter of the circle, that is equal to B. So in conclusion, I found out that according to equation number 1, A over 6 equals to 11 over B. Here we multiplied, because multiplied this equation number 1, and found out that A times B equals to 66. So here we have, so the area of triangle ABC equals to the length of the triangle, the area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width of the rectangle, that is BC. So AB times BC is the length times the width. AB equals to A according to our definition, and BC equals to B according to our definition. Therefore the area of triangle ABCD is AB, and we just right now found out that A times B is 66. So here AB is 66. So in conclusion, we found out that the area of triangle ABCD, the area of rectangle ABCD, it is equal to 66 square units. So in both methods, we arrived to the same result, and we also arrived to the same result in the first question, that we found out that the radius of the circle that is inscribed by triangle ABC, it is equal to 0.6589 units in both methods. Okay? Thank you very much.